Okay, you. So what do we have so far in chapter 3? Chapter 3 is a very long chapter. Yeah. So we have 4 different kind of vector spaces, as we have seen before. Rn, okay, m by n, Pn, polynomial, and functions, continuous functions. So we have Rn means a set of n component. Okay, n of them. Sometimes in some books, they write like this. Okay, so some books, they write the component as vectors or as column. So some authors in the book, they said this is in R3, or Dr. No mentioned this is M3 by 1. Normally, we don't use row or column matrices, but in some cases, it's okay because you have this and looks like a matrix. Yeah, but sometimes we write like this. When you see a comma, so this is in R3. So jangan confuse lah, because some of you refer to some other books, right? Reference books. Okay, and then the second one is the matrix, and then polynomial and function. For each of these, you have to know what is the zero vector, right? The negative of the vector, the regular operation, and multiplication by scalar. Sometimes we change the operation, so you have to follow through, and you have to know the 10 axioms. Our next test would be, let me see the calendar. Next test. 29, yeah, 29 May. I haven't invited all in the Google Calendar, but I will give you the detail later, yeah. So test 2 is the whole of chapter 3 normally, but I will let you know. Test 2, 29 May, 8 p.m. like last time, 8 to 9:15 p.m. in macam hari itulah and our physical class will start in week 10, yeah. Oh yeah, we started. Oh, okay. I have to confirm with the other Dr. Fong whether test 2 will be physical or online, because we have started our class physically on 29 May, right? I already, ya ke tak ni? Tak Oh, no, silap. Week 11. Okay, tengok kalender pun tak betul. Okay, I think it will be online, test 2, because we will start our physical class on 5th June, betul? Right? That is week 11, 4 minggu kan? Okay, betul Alright. Okay. Now, so you have a V as the vector space. And we started to give you S, right? The finite subset of V. V can be any of this, and S is a finite subset of V. Okay, so we have seen linear combination, right? Linear combination of vectors in S. Okay, so we have your V these are all normally is infinite, right? Infinite Rn matrices, they're infinite. But S is finite. So V can be like the whole real numbers, or R2 is infinite. S is finite. We can count how many elements in S. Okay, and then in S we have V1, V2, V3, maybe until Vn or Vk. And when we talk about linear combination, right, we take any y in V. If y is one of the V, is easy, right? You just multiply that V as 1 and the rest is 0, so you get y. When you want to write y as a linear combination, right? Okay, so we say y is a linear combination of the vectors in S. If y is like V2, right? If y is V2, we can just put C2 is 1, the rest is 0, right? So V2 is V2. So we normally will take y not inside S. And then you figure out if there exists this Ci such that y can be written, then we say y is a linear combination of the vectors in S. And how to solve it? We equate, right? System of linear equation. So you can use from chapter 2. And then we start to talk about S spans V. Okay, S spans V. What does it mean? It's very closely related to here. S spans V if for all V in V, okay, for all V in V, there exists Ci in R such that, so I just change this to V. V is a linear combination of the vectors in S. So it's very closely related, right? Just change this y to V. I can do it with y, but since this is given as in the definition for a V, so I just leave it as B. Kalau nak biarkan y je pun, it's okay. So the fact is, actually, S spans V, S spans V if any vectors in V can be written as the linear combination of vectors in S, which means that there exists all the C, right, in the linear combination. So it goes back to chapter 2. Okay, so writing down what it means and then solving, that is what you have to do for this session. So S spans V, this S spans the whole V, if for all V inside the whole vector space, you can write that as a linear combination of the vectors in S. Okay, let's look at some examples. Normally, we don't do number 4, yeah, as I said before, for continuous function, because you don't know what is S. But it is also possible, you'll see. For the others, it's easy. Okay. Okay. Let's go through some examples. I will later give you a hint, yeah? Okay. Oops, sorry. V is R2. Okay, V is R2. S, I call it S1. We look at different examples, yeah. S1 is say 1, 1. Okay. If you want to see what span S is, you have to know what span S means. If S is V1, V2 until Vn, what is span is the linear combination of all. So it's C1 V1 plus C2 V2 plus Cn Vn Ci in R. And I don't give you the Ci, so it's all linear combination. That is the span. Okay. Geometrically, if there is only one, so the span is the set of C11, C in R, which is actually C comma C, C in R. And this gives, if you draw, it's easy to see, 1, 1 is here, right? Okay, so CC is the whole line. Okay, because it's the multiple of 1, 1. Just C11 is multiple of 1, 1. So all this is span S. Okay, so linear combination is just one line, meaning S does not span R2. Okay, another reason why I said that is from geometrically. Yeah? I haven't written the whole proof. Okay, let's try and rewrite. S spans V if for all, this is the key. You have to write the V in terms of any vector in V. Okay, since V is R2, I would say S spans V if there exists, if for all V equal XY in R2, there exists the linear combination, yeah? There exists C in R. Why only C? Because there's only one. Such that C11 equals XY. You see, this is for all. Okay, then we want to find the C. This is the minimum number in the set S, so you don't really see after this I will give you another better example. Yeah? You want to solve for C. Okay, this is quite straightforward, right? You don't need to do all like elementary row operation or Gauss-Jordan because this is straight. You will put CC equal XY, right? You want to see if C exists, but from here, you have C is X, but C is Y. How can C take two different values, right? So there is no solution in general for this particular case. That is quite hard to see because there is only one equation. But suppose I take C, if it does not span, you can see from one example. Say, let V is 1, 2. Right? Like V is 1, 2. I can replace this with 1, 2. Okay. If this is 1, 2, can you find a C multiplied by 1, 1 to get 1, 2? So CC is equal to XY, which is equal to 1, 2. You cannot say C is 1, C is 2, because C is the same C, right? So there is no such C exists. You cannot have 1, 2 because 1, 2 is here, outside the spanning set. Yeah. So in this case, the answer is S does not span R2. Okay. So I show you in two cases. One, I find the span. I find the span. If the span is not R2, it's not R2, it's just a line, right? Then we say S does not span R2. My other way to find it is to solve equation. This is the easier one. You write out the definition. S spans V, the definition, right? If for all V in here that exists, C, you look at how many how many vectors in here, only one, so you just need one C, such that C times this is equal to the V. Yeah. Then you try to solve. Do you have a solution? If there is no solution, then you will say S does not span R2. If there is a solution, then it spans. Okay? Because I show you the minimum number, so you don't really see it. After this, I will show you, like I said, a better example. I call this S2, yeah? S2 with 1, 2. Okay? Now, okay. S2, yeah? 1, 1 and 1, 2. You know, if you draw one is here, 1, 2 is here, right? Any other vector, if you want to draw, maybe here. We learned this at school, right? You can write this as a combination of this, maybe negative, plus this, right? Go to negative and then plus. So it's somehow, how do we draw it? Almost like a lukis. So you draw this maybe to the end, and then you want to draw something parallel, right? So macam ni, and then so negative of this plus negative of this, you will get that. So if it's not have the same, these two does not have the same, what do you call it, angle, right? And then we can find it. Ini yang kita belajar kat sekolah dulu. Okay. So I write the definition. S2, yeah, spans V if for all V equals XY, because this is R2. In R2 that exists. Now how many vectors in S2? 2 of them. So C1, C2 in R, such that V is C1. This is called V1 and V2, yeah? V1 plus C2, V2. So the key is to solve the equation. Find C1, C2. Then you write C1, 1, 1 plus C2, 1, 2 equal. This equal is not anymore a specific number like we try to find under linear combination. We have to write in general, which is equal to XY. So any XY that you are given, you can solve it. So your answer for C1 and C2 depends on XY. Okay. Solve it. So now we can use the Gauss Jordan, yeah? That's wrong, eh? You know, when I was teaching in Lithuania, the hall is big, right? The lecture hall, and the green board I share with you, right? The whole was betul. And then if I need to use this laptop and show the share screen kat atas tu, memang tak padam. Okay. we got lecture hall 2, right? So I think it's much better than this one. Okay, so here I will put 1, 1. I think Dr. No also explained why this is how we get it if we change, right, to the equation, put in the matrix form 1, 2, x, y. Okay, so this is actually the C1 and the C2. When you equate, you multiply C1 plus C2 equal X, and then the other one is C1 plus C2 equals Y, then you put back in matrices. Okay, actually, if you don't have to find C1 and C2, you can stop here and you can say that A is the coefficient matrix and determinant A is 1, which is not 0. So there is a unique solution. There is a unique solution for C1 and C2. So C1 and C2 exist. So S spans V. You'll get full mark, okay? But this you have to explain that since the determinant is not 0, the solution is unique. So C1 and C2 exist because that is what we want to find, right? So S spans V. This is okay. You don't have to solve it, okay? If the question wants you to find C1 and C2, then you have to write longer and solve what is actually C1 and C2. Then you will show one more, 1, 1, x, negative rho 1 plus rho 2, right? So you get 0, 1, negative x plus y. And then one more, okay? I erase, yeah? Okay. One more, yeah? So, negative rho 2 plus rho 1. 0, 1, negative x plus y, 1, 0. So, negative is x plus, so 2x, and negative 1. And then we know that it's span. I want to erase C1 and C2 and replace. Okay, try, yeah? 2x minus y, and then negative x plus y. So 2x minus y minus x plus y is x. Check. 2x minus y minus 2x plus y is y. So check. So what does it mean? It means, padam lah tadi, it means for any xy that you give me, saya lukis balik lah. This is 1, 1, and then 1, 2. Okay. Siti Nur Auni. Can you give me any pair of number? Unmute. Just give me any pair of number.
Any pair, Doctor?
2,
2, 2.
2 senang sangat sebab it's just a multiple of 1, 1.
5, 7.
5, 7, okay? Inilah lebih kurang kan? 5, 7. Yeah? Okay. So I can just plug in and get 5, 7 in terms of 1, 1 and 1, 2. If not, you can go like this and then this, right? This, some multiple of 1, 1, and then this. But if I follow this formula, I will get 5, 7, yeah? 3, 5, 5, 10 minus 7, 3. Okay? 3, 1, 1 plus 5, 7, 2, right? 2, 2, 1, 2. I get 3 plus 2 is 5, 3 plus 4 is 7. Dapat kan? So this means you give me any xy inside R2, I can write that xy in terms of combination of 1, 1 and 1, 2. So this is what it means by S with these two vectors span the whole V. It means any vector in V, you give me any couple, any pair, I can write that as a linear combination of 1, 1 and 1, 2. Yeah, that is what it means by spanning. Okay, so one vector cannot span the whole R2. Just now there is only one vector, right? This one, two vectors can span, but it doesn't mean if I give 2, it will span. There is the hint, and there is a point that I will say later why and how. So you give me any 20,000, 10,000, I can put in here and get you what is the C1 and C2. Because we already have the answer, right? This is C1. So C1 is 2x minus y. C2 is negative x plus y. I get C1 and C2 in terms of x and y. But you cannot get two different answers like just now, right? One more, C is x, C is y, right? So this shows that you have found the C1 and C2 in terms of x and y. Okay. Okay lah, faham lah sikit-sikit kan. Okay, so the key is to solve the equation, right? So just now when I find the determinant, we only know it's span, but I cannot write the linear combination, right? Because I did not solve the equation. Now you can give me any vector I can write in terms of these two. So it's span. Okay, my next question is I want to change the S. Yeah, the S3, yeah, S3 is 1, 1, 2, 2. 1, 1, 2, 2. So I still have two vectors. But you see, if you draw, it is on the same line, right? 1, 1 and 2, 2. So if you span, if you find a linear combination, it will also be on the same line. So you don't span the whole vector space. Okay, so if I put 1, 1 and 2, 2 here, what happened? You will get 0 equal, right? So this I will get negative rho 1 plus rho 2. I will get 1, 2x, 0, 0, negative x plus y. This system is inconsistent. So C1, C2 does not exist. Okay, so there is no C1, C2 because this system is inconsistent, or you can use the rank 1, it's not 2. Then the answer will be S does not span V. Okay. If you draw 1, 1 is here, 2, 2 is here, so the spanning is the whole line. It won't span anything outside. But it's dangerous to use determinant Because if you find the determinant is 0, right? The determinant is 0 can mean there is infinitely many solutions. Infinitely many solution is there is a solution. Okay, so it's very dangerous to use determinant. It can only be used if the determinant is not 0, so it's unique. Okay, that is the end. Remember my tree diagram at the end of chapter 2? So don't just assume, oh, determinant is 0, so there is no solution. No, determinant is 0 can mean there is many solution. Many solution means there is a solution, so it still span. Okay. If you understand this, you can do for the rest, because the rest, you remember for matrices, when we try to solve, it's still like this, right? In a matrix that we can put as a row. Ni siapa yang terbalik-terbalik ni? Nabila? Pening saya nak tengok macam tu. Kamera dia dah terpusing dah. Okay. Polynomial, right? When we take the coefficient, when we want to solve, it's still in this matrix form. So the key is to understand for Rn, then you will understand for all. Okay, let me give you, I didn't follow really the notes, because in the notes, you can try to find the solution for the notes that we share in e-learning, the one with the blank pages, and then try to answer that, and then refer to your complete notes. Yeah, I haven't checked yet if some of you have not picking up your full notes yet, but that is what you should do. Okay, so my number 4. Okay, I will write one more. Okay, so still the same V, I will change as 4. So just now, number 1, I just use one vector. That's not enough, it's not enough. You have to have at least 2. The second one, I have 2, but since they are multiple, oh no, number 2 is okay because they are not multiple. Okay, that is okay. Number 3, there are 2, but it's a multiple, cannot. Number 4, I give you this. More than 2, but still multiple. And number 5, I give you more, but not multiple, not all multiple. Yeah. So you remember the spanning is you take XY, you want to get C1, C2, but this one has to be C1, C2, C3. So S4 spans V, which is R2, if there exists. How many C you calculate in here? C1, C2, C3 in R, such that C1, 1, 1, plus C2, 2, 2, plus C3, 3, 3 equal XY. Oh, I didn't put for all. You can put here or you can put at the end. For all XY in R. Or you can put here if for all here, right? Better put here, or you put it in. So this one you can easily, it translate to this. You don't have to do one by one because it translate to this one, and you will get 0, 0, 0, negative x plus y, right? By using negative R1 plus R2. So this says there is no solution, right? There is no solution. The system has no solution. Your system has no solution. So C1, C2, C3 do not exist. Because this is what we want to see, right? Thus, S does not span V. Don't forget to write out everything. What is asked of you? Okay, what is the conclusion? The system has no solution. This is chapter 2. Okay, so what does it mean? Because this is C1, C2, C3 does not exist. We want it to be exist to span. So S does not span V. Okay. Why do you need this? Okay. If you just draw this, you will see like this, right? 1, 1 is here, 2, 2 is here, 3, 3 is here, right? They're all at the same line. So when you take the C, you will get all this. Okay, just one line that is behind. But it's hard to explain geometrically, but it's just the story behind. Okay, so, but the question can be, not only does S span V, next question can be like this. What is span S4? Okay, what is span S4? If S spans V, I think it's somewhere in the notes. If S spans V, then span S is actually equal to V. Like just now, you have two vectors which has angle. So you find the determinant is not 0. So it spans, meaning actually span of that S is the whole R2. Okay, so if S spans V, span of S is the whole R2. This one is not. So what is the span? The span comes from this. This is the answer. When you solve this, this is the answer. You equal this to 0. Yeah, so you write span of S. Span of S is xy in R2 negative x plus y is 0. Cuba saya besarkan sikit saya punya ni. Nampak ke tak? Uish, kecilnya. Okay. Bolehlah you teropong sikit. Okay, let me read. What is span of S4? Span of S4 is a subset of V. So I write xy in R2 because that is our V, such that I take this equal to 0. Okay, and this gives equal. There are two ways to write this. You can write xy in R2 such that x is y, or you can write xx, x in R, which is this line, right? It is one line, 1 x equals y. So don't leave just like this because it's not really nice. You can write x is y. Sebenarnya letak ni pun dapat full mark lah. But just to see x is y, or you put, since y is x, you put x comma x, right? X comma x is the line, right? Y equal x. That is the span. Okay, for this particular question. Okay. Last question. Tak habis lagi ke soalan yang sama? Okay, I give you different cases so you understand. Okay, and later on I will conclude. There is some generalization that you can do with all of this, but I want you to understand the reasoning first before I give you the general. Ada dia punya rahsia. Okay. Now for S5, the basic thing is use the definition. The question can range. That's why I normally don't like to share past year's questions, or because I already put everything that you need to know in the example, in the exercise. So do just that, because the questions can change from these different vectors. Okay, once you understand, I'm sure. But to write as exercise is okay. Dr. No also shares some questions, right? So you just do, you want to write it again, S5, span V, which is R2, if for all V equals XY in V, that exists 1, 2, 3, C1, C2, C3 in R, such that C1, 1, 1 plus C2, 1, 2 plus C3, 1, 3 equal XY. Okay, so this is the same definition that I used before. Given the S5 and given the vector space, V is R2. Okay, so you write S5, span the vector space V equals to R2 if for all vectors V in R2, which is XY, don't worry if you write R2, if you write V, it's okay. That exists, you want to solve this equation by finding C1, C2, C3, the coefficient in R. Are they real numbers such that you multiply this C1 times V1, C2, V2, C3, V3, and you equal to the whole XY in V, which is R2. The next one is chapter 2. Then you want to solve 1, 1, 1, 2, 1, 3, XY. In this case, the coefficient matrix is not n by n, right? Just now it's 2 by 2. So I said you can check the answer by uniqueness if the determinant can be found. This one is not even square. You cannot find the determinant, right? So you have to solve this and see whether C1, C2, C3 exists. Okay, so this is C1, C2, C3. I know. This is not 1, 3. This is 3, 4. Cikgu kata apa? Just to make sure that you are awake. Berhenti je kan? Okay. Okay, so okay lah. Maknanya tak lelap lah ni. Okay, so I want to solve this. Negative R1 plus R2. So what do you get? 1, 1, 3, X. Okay, 0, 1, 1, negative X plus Y. Okay, up to this point, you can already see this is the echelon form, right? So there is one here, there is one here. This is a free variable. So there's a infinitely many solution, but there is a solution. So C1, C2 exists, C1, C2, C3 exists, and it's span. Okay, and it's span. If it's span, that means so there is infinitely many solution, or there is a solution. There is infinitely many solution. So if there is infinitely many solution, so you will say C1, C2, C3 exists. But don't just stop exist. You have to answer the question. So S5 spans V because it exists. Okay, that is my whole question. At the end, if it exists, what is span? So you can write span S5 is actually the whole R2. Actually, you have more than enough. You need just 2, but you have 3. So that is why it is still possible to find the solution. If you really want to find the linear combination, you have to solve. Okay, but it's not asked in here. If you really want to find what is C1, C2, C3, then you just do another one and then you find C1, C2. But it's more complicated because C3 is free. So you can get like so many solutions. And also this one change regarding the X or the Y. What I meant is that you don't need this. You don't need a 3, 4. With these 2, you can already find the span like before. We go back to question number 2. Okay, so giving additional vector does not change the spanning. 2 is already enough. So that is what you need to know about spanning for Rn. So in conclusion, what we have so far is, okay, so if V is Rn, okay, and S is given to be V1, V2, V3, up until Vk, okay, like just now, I give you N is 2, and then I give you K, 1, 2, 3, right? So the first case is when K is less than N, right? Like I give you N is 2, K is 1. Then S does not span V. Not enough, okay? Not enough. Number 2, if K is N, like just now, when we get 2, 2, right? So you can find the determinant. If the determinant is not 0, then S spans B. This is very similar to chapter 2. And because of the solution, if the determinant is 0, we don't know. Because it can be infinite or it can be no solution. So you have to follow and using the Gauss. Okay. The third one, when K is bigger than N, it can be both. Like I have shown you before, we don't know. Okay, so the easiest way is number 1 and number 2 when the determinant is not 0. So I've given you 5 cases before to show you that if you have R2 and S has only 1 vector, not enough, does not span. And the spanning, you have to go through the matrix and find the last row in echelon form, equal that to 0 to find the span. If the answer is yes, it span, that means the span is the whole V. Okay, so this is given already in your book, lecture notes, page 3.2. Theorem 3.2, page 169 in this here. Here you have to check for the PDF one. It says, suppose S I use the U1, U2 until UM, but it's okay. Yeah. If it is less, it does not span. If it's equal, and I say for this particular one, it's a special because we want to have enough. It does not span. Oh, so this is easy. If it's equal to 0. And that is an example to find the span. Okay. More example. Number 4 is less. Then find the span. And then I give you a 2 by 2 matrix. And I give you polynomial. Okay. So if I give you this, for example, I will not solve it, but I'll just show you how you will be given for matrix. So for matrix, say V is M2 by 2. Okay. You need 4. You need at least 4 to span. Yeah, because the dimension is 2 times 2. If it's n by n, you need n squared to span. So if you are given just 1 like this, it does not span. You have to have at least 4. For example, I change the 1 here, 1, 1, 1, 1. So this is the easiest set S that can span M2 cross 2. Because if you multiply by C1, C2, C3, C4, which is equal to any matrix in M2 by 2, call it X, Y, Z, W. Any 2 by 2 matrix, right? In 2 by 2 matrix. Then very easy, you will get C1 is X, C2 is Y, C3 is Z, C4 is W. No need to write all the matrices, right? Because you can just. So like 1, 2, 3, 4 is 1 times this plus 2 times this plus 3 times this plus 4 times this. Part of chapter 3 is about linearly independence and also basis. Yeah. So I think one of the hardest part is the spanning, to see whether it spans by understanding the definition. This one is very similar to linear combination or spanning in the sense that you equate it to 0. Okay, you equal the linear combination to 0 to solve homogeneous system of linear equation. Homogeneous system of linear equation, if you remember, is AX equals 0, right? So suppose S is, now I use U1, U2. The same thing if you use V, UN. Suppose S is U1 until the UN, a subset of a vector space V. or you use M. Doesn't matter. Because I want to use N as the dimension of V. Okay. Then S is called linearly independent if C1, if C1U1 plus C2U2 plus C3U3 plus CMUM equals 0, but this 0 is the zero vector, implies, you know, all the C's, they are real numbers, yeah? Implies all the C1, C2, they are all 0. Okay, that's it. If they are not 0, we call it linearly dependent. Okay. So I will say S is linearly dependent if there exists Ci in R not all 0. Okay. Such that the same thing, copy paste. Okay, so the key is to solve the equation and see whether the C's, are they all 0 or not? Okay, if they all have to be 0, linearly independent. If some of them are not 0, it's linearly dependent. Okay. Now we go to the example. Like this. There's also the theorem later, but we look at based on the definition first. What is the vector space? So you look at the element inside the set. It has 2 components, right? So V is R2. If you don't know the V, then you will not be able to write out the 0 vector. So you have to know the V, and the V dapat dalam pula 1, 2, 3, 4. The Rn, the Pn, the matrix, yeah, and the 0 function. Okay, so you want to find the C multiplied by 1, 1 equal 0, 0. Solve for C. What is the answer? Very easy, right? You don't have to do. So you get C is 0. Okay. You take the C, multiply by there is only 1, so just 1 C. This is always the 0 vector. Okay. And for R2 is 0. So CC equals 0, 0. So C is 0, right? Once you get all C is 0, thus S is linearly independent. That's it. Okay. What if you want to see using matrix, right? What happened? Okay, so I will write, padam dulu ya, tak muat. So, how do you solve this? CC equals 0, 0. Or this, like usual, we write like this, right? It's too easy, sometimes difficult to see. The 1, 1, we write ke bawah kan? Okay, there's a C here, right? Then you do negative R1 plus R2. Then you will get 1, 0, negative 1 and add. And you get C is 0. Dia menyusahkan diri lah. Senang pun nak buat tu. Okay. But just in case you are wondering how to do it using matrix, because this is too easy. So this is okay, right? 0 equal is 0. And when you read this is C equals 0. So in this case, yes, the answer S is linearly independent. Okay. So there is a theorem. It says if there is only one vector, it's always linearly independent. Okay, if there is only one vector, it is always linearly independent. Because one vector that is not 0, yeah? I can prove that in general. So, alamak, ni mungkin boleh jadi soalan test 2. Show that S equals V or U in V, U is not 0, is always linearly independent. Okay, any set that has only one non-zero vector is always linearly independent. Or the question can be asked in all words in a sentence. Suppose show that a set consisting only one non-zero vector is linearly independent. Then you have to write out. This is actually the set. Show that a set consisting of only one non-zero vector is linearly independent. So what you should do is you multiply C by U equal to 0. So this is the proof. Because of the definition, you multiply by C, U equal to 0. Since U is not 0, that is from the question, right? Since U is not 0, you multiply C by not 0, you want to get it equal to 0. So C must be 0. So since C is 0 by definition, its S is linearly independent. That's it. Okay. So after this, if you are given only one vector in a set, it's linearly independent. Okay. Next. Kita cuba tengok soalan dalam nota. Okay, so you have the space to look. Does not span, linearly independent. Okay. In this, you already get the right notes, yeah? Exercise 12 here. 187. S equal 1301 3903. So if you are not given the V, this looks like a matrix, right? So this is a matrix 2 by 2. Okay, first there's not 1, there's 2. So it might be independent or dependent. Okay. Now, I give you a hint. If there are 2, one is a multiple of the other one, it's dependent. If there are 2, one is a multiple of the other one, it is dependent. If there are 2, one is not a multiple of the other one, It's independent. Okay, but you cannot use this because you have to prove in general, but that's a hint that you can think about. So this is actually 3 times this, right? So it is actually dependent. Okay, I will write out before I use the definition shortcut. Yeah, U1, this is U1, 3U1 equals U2. This is U1, this is U2. 3U1 equals U2. So I get 3U1 minus U2 equal 0. See the C? C1 is 3, C2 is -1, which is not 0, but the linear combination is 0. So it is linearly dependent by the definition. Okay, put this aside first. I will write out from scratch, yeah? Write out the definition and see what happened to the C or not. Padam dulu. Okay, because I will write again. Okay, so find C1, C2 in R such that C1 U1 plus C2 U2 equals 0. Okay, so C1 times 1301 plus C2 3903 equals, that's why you need to know your vector space. Yeah, you need to know your vector space. So that is the 0 vector. So you can multiply out, you can add, and then you can equate, right? Or you can just write out 1301 3903. I normally write in terms of row. 1301 3903 and then 0000. This is the C1 and the C2. You cannot just take the first 2 rows. You have to solve for all, because sometimes you will see whether they exist or, but they always exist, whether it's unique or many solution, right? You remember chapter 2? If you have AX equals 0, there is always a solution, because when you put X equals 0, is 0. So there is no such thing as no solution. Unique solution or many solution. If it is a unique solution, this is what we call a trivial solution. Meaning all the answers is 0, right? Meaning it's linearly independent because all answer, they're all 0. Okay, you multiply A by 0, definitely is 0. But if it's many solution, when you want to do chapter 3 with this, it's linearly dependent. So from this, you can relate chapter 2 with this part. For this one, you cannot find using the determinant because it's not 4 by 4. Right? So you will do the elementary row operation. So -3 row 1 plus row 2. That's already 0. Negative row 1 plus row 4. That's the same, right? Okay. Okay, so what do you get? 1, 3, 0. -3 and add, -3 and add, 0, 0, 0. 0, 0, 0. What happened? They're all 0. So this is C1, C2. Don't forget chapter 2. So you get C1 plus 3, C2 is 0. C2 is free. C2 is free. So you can write C1 is negative 3, C2 which is negative 3, K. So when you put the answer, if negative 3K, K. This means many solution. Okay? Many solution means not all C is 0. Okay? So S is linearly dependent. Write out one by one by one. First, there's a free variable. Then there's a solution. This is optional. But we need this if we want to write out what is the linear combination. So many solution, not all 0. So this is the final answer. Okay, linearly dependent. And if I put K is 1, if I put K is 1, this gives me negative 3 and 1. Remember, just now I put the answer. Negative 3 plus 1 or 3 minus 1, right? The same thing. Actually, you can choose negative 6 plus 2. So there are many solutions, but not all 0. Okay. So I give you a shortcut earlier because I can see that V2 is 3V1. Sometimes you don't see this, you need to solve this. But the key is, what is your answer? Whether you get all 0 or you get some not zeros. Not zeros means linearly dependent. Okay. I think this is clear, a clear solution. Okay, once you write out the definition of linearly independent. Okay. Okay. Ni yang tak nampak muka video ni okey ke tak? Okay, let me see. Last page. Okay, Vineta, you are in the last box. And okay, from that one. Okay, now go to the next question. Very close, but I changed this to 2402. It is not if this is 6, right? If this is 6, then it's a double, but it's not. It's not a multiple. So if you want to redo this, okay, if you want to redo this, I will erase, yeah. Okay, if you want to redo this C1 and C2, 1301 and 2402, you will get, okay, let's see. This is always 0 because it's homogeneous, so it's easy. We don't have to calculate. Okay, so 1, 2, right? 1301, 2402, so it's 1, 2, negative 3 and add, negative 2, 0, 0, 0, negative 0 and add 0, 0, 0. So from here, it doesn't matter, but you need to do once more. That is, so you can do negative a half. Oops, negative a half. You'll get 0, 1. Then you will get 1, 0, 0, 1, right? Forget about this because this is just 0, 0. So you will get 1, 0, 0, 0, 1, 0. So you will get C1 equals C2 equals 0. So this is linearly independent. Okay, linearly independent. So if you have two vectors, one is not a multiple of another one, they will be linearly independent. But you have to show this way. Okay. Okay. Number 3 is a polynomial. Now I want to show you. Before you need to do the spanning, but it's the same. Let me just show one for the polynomial. S is P1, P2, P3. So P1T is 1, P2T is T, P3T is 4 minus T. Okay. Still the same. Find C1, C2, C3 in R because they're 1, 2, 3. Okay, such that C1, C2, C3, U3 equals 0. Polynomial 0 is just a 0. Okay, so we will write C1 times 1 plus C2 times T plus C3 times 4 minus T is 0. Okay, I've never shown you this, I believe, how to transform into matrix. Maybe Dr. Noor has mentioned this, but make it consistent. If you do, there's only 1 and T, right? Okay, there's only 1 and T. And this is like 1 and T. If it's T first, then you probably want to do T first, T and 1. So I take this 1 is 1, 0, T is 0, 1, 4 minus T is 4, negative 1. And then it's always 0, 0. So I take the coefficient. Even if you multiply out, you will do C1 plus C2T plus 4C3 equals 0. And then you take the coefficient equals 0. It will be the same. So I will take this 1. I put 1, 0. There is no T. I take this T is 0, 1. And I take this 4 minus T is 4 minus 1. So this is actually, there is a C1, C2, C3. Okay. Then you can see there's a free variable, right? There's a free variable. Then definitely many solution. So it's dependent. I didn't do anything, but I can see the rank, right? Because this is in the echelon form. And also row echelon matrix actually, because you don't have to do anything. If you look, the leading one down is already 0. Second row, the leading one, that's already 0. And there is no third row. So no need to worry about this one. So C3 is free. C3 is a free variable. So there is many solutions. Thus, not all CI is 0. S is linearly dependent. Okay. So the secret is, if the number of vectors is more than the dimension, okay, the number of vectors, 1, 2, 3, the dimension of P2, this is P2, yeah, is n plus 1, Pn plus 1. This is in P2. Why do I know P2? Because polynomial is T to the 1, T to the 1. So it's not P2, P1. Polynomial of degree n, yeah, T to the 1. And the dimension of P1 is, the dimension of Pn is n plus 1. Okay, I will mention about this again later, yeah. Okay, so don't worry about the dimension, about the, later on I will say it again after we go to the basis, okay. Your job is to try as many. I have one more for R3, okay. Theorem 3.3. If you have m number of vectors in S and m is bigger than n, this is what I just mentioned earlier. S is U1, U2 until UM. Okay. I talk about Rn first. Okay. If m is bigger than n, then S is linearly dependent. Just now, when I said if m is only 1 and it's a non-zero vector, it's independent, right? If m is 1 and it's not, because if a zero vector, if there is only 1 and it's a zero vector, it's dependent. Why? Because you multiply by C, C doesn't need to be 0, right? Because it's already a zero vector inside. So just put in the definition if you're not sure. If you have a zero vector here, it's always dependent. Before this question is in the final, if you have a set with only zero vectors, show that it is linearly dependent. Because when you multiply by C, you want to get equal to 0. That's already a zero vector. C can be not 0. Okay, so dependent. If you have just 1, and this is not a zero vector, this is linearly independent. Right? Because when you multiply C by U, you want it equal to be zero vector. C has to be 0. So it's linearly independent. Okay. If M is N, the same number, yeah, then this is the coefficient matrix, yeah, after we put into matrix, is not 0, implies S is independent. This is 0, implies S is dependent. So if you have the right number and you can find the determinant, then you go back to chapter 1. You can do using determinant. If I give you this, you can easily say this is independent, right? Because the determinant is not 0. If I give you another one, One reason because one is the multiple of another one. Another reason is because the determinant is 0. So this is dependent. Okay, I know there's too much to understand, dissolve lagi, but go through the notes and go through the examples. It's not that hard. Just need to understand the definition and how to apply. Because from these two, then we go to the last part of this section, which is a basis. And to show something is a basis, you have to show that it's span and it is linearly independent. That's why we need these two. So I will give you the last part of this definition. S is a basis of V if S spans V and S is linearly independent. Let me write out the set S and V of dimension n. Okay, the vector space that we have Rn has dimension n. Pn has dimension n plus 1. The matrix m by n has dimension m times n. Okay. For function, we don't have a basis for the whole function. So we normally don't talk about the function for the basis. So for this set, you have to have enough number to be a basis. If the number is less, it does not span. Not enough to span. I have showed you before, right? If 1 to R2, it does not enough to span. If m is bigger than n, it will be linearly dependent. If it's less, you don't know whether independent or dependent. It can be both. Okay, so don't assume. If m is less than n, it can be independent, it can be dependent. If m is less than n, it does not span. If m is bigger than n, it can span or not. You don't know. Okay, I have shown you before, right? You have 3 for R2, 1, 1, 2, 2, 3, 3. It's bigger, but it does not span because it's all in the same line. So you cannot say anything. If m is n, and this is not 0, then it is a basis. But you have to show that S spans V and S linearly independent. You cannot just show by, okay, the determinant is this, then automatically you say it's a basis. No, you have to write out what it means. It's a basis if it spans and also it's linearly independent. What does it mean by span? You write out C1, V1 equal to V and show Ci exists. Okay, in showing it exists, you can do in any way solving linear equation like in chapter 2, the 4 methods. But there has to be an explanation showing that the C exists. And also by this one, because this is replacing the V in here by 0. Okay, let me write the definition. S spans V if for all V in V that exists Ci in R such that C1 U1 plus C2 U2 plus Cm Um is V, right? S is linearly independent if C1 U1 plus C2 U2 plus Cm equals 0 implies C1 equals C2 equal Cm equals 0. This is a 0 in real number. 0 is in real number. You compare these two. They are the same equation, just that the V becomes 0. Okay, so if you have started proving by spanning and you want to show it's linearly independent, you just replace the x, y, z with 0, 0, 0. Then you get your answer. So this part is basically will be covered by this part when you show it's spanning. Okay, you will see this when we do the next class. So before we go to the next class, you have the notes and you have the weekend. Asyik nak beraya je, tentang 2 tahun tak raya. Then I will ask you to do all the exercises. Then when we come back, I will call your name to show me your answer. Tapi dah ada kat dalam tu kan. Saya tanya daripada exercise belakang lah, not exercise inside the notes. The exercise in the back. But please do exercise 13 as mentioned in the PDF, whether it's dependent or not. And if you have any question that you cannot solve it, please ask during class. Okay, then I will solve. Otherwise, I will ask you to explain kalau ada soalan kan. And then I mentioned also page 194. I have mentioned earlier, but I put it there. If there is a 0 vector, which is a multiple linear combination, okay? And there's also exercise independent or not. I don't want you to just count. I want you to write out and solve for the C. Okay, but you know in advance, there's only 2 or there's only 1 or there's so many, right? You know the answer. But I want to see you write out using the definition. And then you can start with the basis. Okay. The dimension I already mentioned. I already mentioned about all the theorems. Okay, and exercise 14 is a very good exercise. The same question from the example before, that to show whether it's a basis or not. If it does not span or it is not linearly independent, it is not a basis. So to show that something is not a basis, you can choose either one. Okay, either one. If I already erase, you see too many, right? You see too many or too little, not enough, then it is not a basis. Then I will start on the next, which is coordinate vector. So for say R3, the dimension is 3. So you would need 3 vectors. to be a basis. If it is less, it does not span. If it is more, it is not independent. Not independent means dependent. Okay, but since the definition of basis is independent, your answer should be it is not linearly independent. Use the word linearly independent. Yes or no? Understand? Unless the question show whether this is dependent or not. English is weird, right? The opposite, the acronym of linearly independent is dependent, but we want to check whether it is linearly independent or not. So if it's 3 is possibly a basis. If like if P2, you need 3 also. If you have M like 3 by 2, you only have 4 in S, definitely not a basis because you need at least 6. If it's 7, too many, it's dependent. If it's only 4 or too little, cannot span. All right.